On February 10, 2025, scientists at Rosatom, Russia's state nuclear energy corporation, announced a significant advancement in space propulsion technology with the unveiling of a plasma electric rocket engine. This innovative engine is touted to have the capability to propel spacecraft to Mars in just 1 to 2 months, a stark contrast to the nearly year-long journeys typical of existing spacecraft. Overview of the plasma electric rocket engine. The plasma electric rocket engine operates using a magnetic plasma accelerator diverging from the traditional rocket engines that rely on fuel combustion. This new propulsion system enhances efficiency and speed, leveraging charged particles accelerated to incredible velocities. According to Igor Byryalin, a junior researcher at Rosatom's Scientific Institute in Troitsk, the mechanism involves 2 electrodes through which charged particles are passed while a high voltage is applied. This process generates a magnetic field that propels the particles, resulting in thrust. Key specifications and features. 1. High-speed propulsion. The engine can accelerate particles, primarily electrons and protons, to speeds of up to 100 km per second, approximately 62 miles per second. Traditional rocket engines, by comparison, typically achieve maximum speeds around 4.5 km per second due to the limitations of combustion propulsion. 2. Power output. The prototype engine has a power output of approximately 300 kilowatts and operates in a pulse periodic mode, which allows for better management of energy and thrust production. 3. Testing and development. A specialized experimental facility measuring 14 meters in length and 4 meters in diameter has been constructed to simulate space conditions for extensive ground testing. The prototype will undergo rigorous trials to refine its operational capabilities, with plans for a flight model to be ready by 2030. For cosmic radiation mitigation, one of the critical advantages of this technology is the potential reduction in astronaut exposure to cosmic radiation. By shortening the travel time to Mars to 30 to 60 days, the risks associated with prolonged exposure during a longer journey are significantly minimized. Implications for future space missions. The introduction of Rosatom's plasma electric rocket engine represents a transformative shift in the feasibility and safety of interplanetary travel. Current missions to Mars are fraught with challenges, particularly the long duration that increases the risk of radiation exposure for astronauts. By dramatically reducing this journey time, the plasma engine not only enhances mission safety but also opens the door for more frequent and ambitious missions to Mars and potentially beyond. The technology could also pave the way for further advancements in space exploration, as noted by Alexei Voronov, First Deputy General Director for Science at the Troitsk Institute. The development of this propulsion system could lead to interplanetary trips becoming significantly faster, making locations beyond the solar system more accessible in the future. Testing and future prospects. While the plasma electric rocket engine shows promising capabilities, the initial stages of its implementation will still rely on traditional chemical rockets for launching spacecraft into orbit. After reaching a designated orbit, the plasma engine would take over to facilitate travel to Mars and potentially other destinations in space. The timeline for completion of a flight model is set for 2030 following exhaustive testing and refinement of the prototype. As other space agencies, including those in Europe and the United States, explore similar advancements in propulsion technology, the competition and collaboration in this field could accelerate the pace of human exploration of Mars and beyond. Conclusion. The unveiling of Rosatom's plasma electric rocket engine is a significant milestone in the realm of space exploration. This technology promises to revolutionize how we approach interplanetary travel, making missions to Mars not only faster but also safer for astronauts. As we look toward the future, the successful development and deployment of such advanced propulsion systems could herald a new era of exploration beyond our planet, potentially unlocking the mysteries of the universe and expanding humanity's reach into the cosmos. The announcement by Rosatom regarding their plasma electric rocket engine presents several counterintuitive elements worth noting. 1. Speed versus distance.
While the claim that spacecraft could reach Mars in just 1 to 2 months seems revolutionary, it contrasts sharply with the current understanding of space travel. Typically, reaching Mars takes nearly a year with traditional propulsion methods. The concept of achieving such speeds up to 100 kilometers per second raises questions about the physical and engineering challenges involved, including how to sustain such speeds over vast distances without encountering significant obstacles or the need for deceleration. 2. Reduced risk of cosmic radiation. The assertion that shorter travel times would reduce astronaut exposure to cosmic radiation is logical at first glance. However, it may overlook the complexities of radiation exposure in space. Astronauts are still exposed to radiation during the launch phase, and the spacecraft's protective measures against radiation during high-speed travel must also be considered. If the spacecraft travels faster, it might also encounter higher energy particles that could pose additional risks. Countering the intended benefits of reduced travel time. 3. Dependency on traditional launch methods. The reliance on traditional chemical rockets for the initial launch into orbit before switching to the plasma engine is somewhat counterintuitive. It suggests that despite advancements in propulsion technology, the industry is still heavily dependent on existing technologies for the critical first phase of space travel. This could imply that the new technology, while promising, is not yet fully capable of independent operation from conventional systems. 4. Complexity of engine operation. The mechanism of operation, which involves generating a magnetic field to propel charged particles, raises questions about the complexity and practical implementation of such systems in actual space missions. The idea that electrical energy can be almost entirely converted into motion without significant thermal overload is appealing, but may not account for the challenges of energy efficiency, heat dissipation, and the long-term reliability of components under operational stresses. 5. Potential for interstellar travel. The statement that this technology could extend beyond Mars, potentially making interstellar travel more feasible, is remarkably ambitious. It implies that the same principles could be scaled up for much longer distances, which poses numerous challenges not only in propulsion but also in life support, navigation, and the physical effects of extended space travel on human crews. The leap from interplanetary to interstellar travel is monumental and often underestimated in terms of the technological and biological hurdles that must be overcome. 6. Technical specifications and feasibility. While the engine's reported thrust of about 6 N and power output of approximately 300 kilowatts may seem adequate, it raises concerns about the overall feasibility of such a propulsion system. The ability to generate sufficient thrust to achieve and maintain high speeds over the required distance within a practical timeframe. While managing energy consumption is a complex engineering challenge that may not be fully addressed in the current prototype phase, these counterintuitive aspects highlight the complexities and challenges inherent in advancing space travel technology, particularly in making bold claims about the future capabilities of new propulsion systems. The recent announcement by scientists at Rosatom regarding a plasma electric rocket engine capable of reaching Mars in just 1 to 2 months is a significant development in the field of space exploration. While the primary features and implications of this technology have been covered, several critical aspects may be overlooked by the general audience, which are worth highlighting for their potential impact on the future of interplanetary travel. 1. Technical advancements in propulsion systems. The significance of the engine's mechanism of operation should not be understated. It operates using a magnetic plasma accelerator, which fundamentally differs from traditional chemical propulsion systems. This means that instead of relying on combustion, which limits maximum velocity to approximately 4.5 kilometers per second, this plasma engine can accelerate particles to speeds of up to 100 kilometers per second. This remarkable increase in speed not only enhances the efficiency of space travel but also opens the door for more ambitious missions beyond Mars. Why it matters. The transition from chemical to electric propulsion represents a paradigm shift in aerospace engineering.
It suggests a new realm of possibilities for spacecraft design and mission architecture, paving the way for deep space exploration missions that were previously deemed impractical due to time constraints and safety concerns. 2. Mitigation of cosmic radiation risks. One of the critical issues faced during long-duration space missions is exposure to cosmic radiation, which can pose severe health risks to astronauts. Current missions to Mars can last nearly a year, significantly increasing the risk of radiation exposure. By reducing travel time to 30 to 60 days, this new technology could substantially mitigate these risks. Why it matters: the health and safety of astronauts are paramount for future manned missions to Mars and beyond. By addressing the radiation exposure challenge, this technology not only protects crew members but also enhances the feasibility of long-duration missions, potentially increasing public support and investment in space exploration. 3. Interplanetary travel efficiency. The ability to conduct interplanetary travel more efficiently could revolutionize our approach to space exploration. With the potential to reach not just Mars but also other celestial bodies more rapidly, this technology may facilitate more frequent and diverse missions, including cargo transport and scientific exploration. Why it matters: enhanced efficiency in space travel could lead to a more robust and sustainable human presence in space. It could enable collaborative international missions, foster advancements in technology through competition, and enhance scientific understanding of our solar system and beyond. 4. Future applications beyond Mars. While the immediate focus is on Mars, the implications of this technology extend far beyond. The ability to reach Mars in such a short time frame lays the groundwork for potential missions to other planets or even moons, as well as deeper exploration of the solar system. Why it matters: the prospect of interstellar travel, while still largely theoretical, becomes more tangible with advancements in propulsion technology. Such capabilities could inspire future generations of scientists and engineers to pursue careers in aerospace, leading to innovations that could benefit other fields as well. 5. Economic and strategic considerations. The development of this propulsion technology also has broader economic and geopolitical implications. Countries that lead in space technology can gain significant advantages in terms of scientific prestige, military capabilities, and economic opportunities related to space exploration and exploitation of extraterrestrial resources. Why it matters: as nations continue to invest in space exploration, the competition for leadership in this domain will intensify. This could spur increased funding for research and development, as well as collaboration among countries to address shared challenges in space. 6. Experimental testing and validation. The establishment of a specialized experimental facility for testing the plasma engine prototype is crucial. This facility, designed to simulate space conditions, will be instrumental in refining the engine's capabilities and ensuring its reliability for future missions. Why it matters: the rigorous testing phase is essential not only for the success of this specific project but also for the validation of new technologies in aerospace engineering. Successful testing could inspire confidence in similar technologies and lead to a broader acceptance of electric propulsion systems in future spacecraft designs. Conclusion. The unveiling of Rosatom's plasma electric rocket engine represents a significant milestone in propulsion technology with far-reaching implications for the future of space exploration. While the headline features of the engine's capabilities and potential applications are noteworthy, it is the overlooked details, such as the technical advancements, mitigation of radiation risks, future applications, and economic considerations, that truly underscore the significance of this development. These aspects not only reflect the potential for enhanced interplanetary travel but also highlight the importance of continued investment in space technology and exploration, shaping the future of humanity's presence in space. The unveiling of Rosatom's plasma electric rocket engine represents a significant milestone in space exploration technology. This innovation promises to drastically reduce travel time to Mars, potentially allowing spacecraft to reach the planet in just 1 to 2 months.
Here are 4 valuable points for in-depth analysis and discussion. 1. Technological mechanism and advancements in propulsion. The plasma electric rocket engine operates on a fundamentally different principle compared to traditional rocket engines. Traditional propulsion methods rely on combustion, which limits maximum velocity to approximately 4.5 km per second. In contrast, Rosatom's engine utilizes a magnetic plasma accelerator that propels charged particles, specifically electrons and protons, through high-voltage electrodes, achieving speeds of up to 100 km per second. This remarkable advancement not only enhances thrust capabilities but also opens the door to more efficient interplanetary travel. The implications of such technology extend beyond Mars missions, potentially enabling faster travel to other celestial bodies and even locations beyond the solar system. Discussion could delve deeper into the physics behind plasma propulsion technology and how it compares to existing propulsion systems. 2. Safety and health benefits for astronauts. Reducing the travel time to Mars from nearly a year to just 30 to 60 days significantly mitigates the health risks associated with prolonged exposure to cosmic radiation, a major concern for astronauts on long-duration missions. Current missions face the challenge of radiation exposure, which can lead to serious health issues, including increased cancer risk. The plasma electric engine's ability to shorten mission duration enhances the safety of astronauts, allowing for more feasible manned missions to Mars. This point opens up a broader discussion on astronaut health and space travel, including the biological impact of cosmic radiation and other environmental factors encountered during long-term space missions. 3. Testing and development timeline. The development of the plasma electric rocket engine includes the construction of a specialized experimental facility to simulate space conditions for extensive ground testing. A flight model is expected by 2030, with initial launches still relying on traditional chemical rockets for orbital insertion. The timeline for this technology raises questions about the pace of innovation in space exploration and the collaboration between governmental and private sectors. Analyzing the project's milestones, potential delays, and funding challenges could provide insights into the developmental landscape of advanced space technologies. 4. Broader implications for space exploration. The plasma electric rocket engine not only has the potential to revolutionize travel to Mars but also to facilitate missions to other planets and even beyond the solar system. With plans for interplanetary missions becoming more ambitious, this technology could enable human exploration of locations previously deemed unreachable. Furthermore, the implications extend to the economic aspects of space travel, including the possibilities of cargo transport between planets and the potential for establishing human settlements on Mars. A discussion could explore the future of interplanetary travel, the role of international collaboration, and the long-term vision for human presence in space. In conclusion, Rosatom's plasma electric rocket engine is poised to transform the landscape of space travel. Each of these points not only highlights the technological innovations involved but also opens avenues for broader discussions on safety, development timelines, and future exploration possibilities. 1. Project Orion, 1950s to 1960s. Project Orion was a study conducted by the United States during the Cold War aimed at developing a spacecraft propelled by nuclear pulse propulsion. The concept involved detonating nuclear bombs behind the spacecraft to propel it forward, potentially allowing for journeys to Mars in a matter of weeks. While the project showcased the potential for revolutionary space travel, it was ultimately abandoned due to technical challenges, concerns about nuclear fallout, and international treaties against nuclear testing in space. 2. NASA's vision for space exploration, 2004. In 2004, NASA unveiled its vision for space exploration, which included plans for human missions to Mars. The initiative emphasized the need for advanced propulsion technologies to shorten travel times and increase mission feasibility. NASA explored various propulsion concepts, including nuclear thermal and solar electric propulsion, to achieve faster transit times to Mars, highlighting the significant risks associated with long-duration space travel such as cosmic radiation exposure. 3. Mars Direct 1989, proposed by Robert Zubrin. Mars Direct is a mission architecture that focuses on sending humans to Mars using existing technology. The plan emphasizes the use of in-situ resource utilization (ISRU) to produce fuel on Mars, allowing for a more sustainable approach to space exploration. While not centered on advanced propulsion systems, the concept addresses the challenges of long-duration spaceflight such as radiation exposure and the psychological effects of isolation. Paralleling the goals of the new plasma electric rocket engine developed by Rosatom. The unveiling of Rosatom's plasma electric rocket engine marks a significant milestone in space exploration technology with the potential to revolutionize interplanetary travel. Here's an outlook on the future implications and developments stemming from this innovation over the next decade and beyond. Short-term developments 2025 to 2030. 1. Prototype testing and refinement. The immediate focus will be on extensive ground testing of the plasma engine prototype. By 2030, Rosatom aims to finalize a flight model capable of operating in space conditions. This phase will involve rigorous validation to ensure reliability and safety critical for future manned missions to Mars. 2. Integration with existing technology. Initial launches will still rely on traditional chemical rockets to reach orbit. The plasma engine will engage post-orbit, indicating a transitional phase where hybrid propulsion systems are employed. This dual-phase approach will likely lead to refinements in both chemical and plasma propulsion technologies. 3. International collaboration. As countries like the USA and members of the European Space Agency pursue similar advancements, collaborative projects may emerge. Sharing data and resources could accelerate development timelines and enhance safety protocols. Midterm implications 2030 to 2040. 1. Manned missions to Mars. With reduced travel times of 1 to 2 months, crewed missions to Mars become more feasible. This could lead to sustained human presence on Mars, facilitating scientific research and exploration. The first manned mission may occur in the 2030s, driven by advancements in life support systems and habitat technologies developed in parallel with propulsion advancements. 2. Expansion of space infrastructure. The success of plasma propulsion could lead to the establishment of a framework for interplanetary transport systems. The development of space tugs, which could transport cargo between planets using plasma engines, may be on the horizon. This infrastructure will be essential for supporting Mars colonization efforts and establishing supply lines for future missions. 3. Increased commercial interest. The faster travel times could attract private sector investment in space tourism and commercial exploration. Companies may seek to leverage the technology for expeditions to Mars or beyond, potentially leading to a new era of commercial spaceflight. Long-term vision 2040 and beyond. 1. Exploration beyond Mars. The implications of the plasma rocket technology extend beyond Mars. With enhanced capabilities, missions to outer planets and even beyond the solar system may become viable. The possibility of sending unmanned probes to distant exoplanets could revolutionize our understanding of the universe. 2. Technological spin-offs. The engineering challenges overcome in developing plasma propulsion may yield technological advancements with applications on Earth, particularly in energy generation and materials science. Innovations in high-efficiency motors and energy conversion could benefit various industries, fostering advancements in renewable energy technologies. 3. Deep space colonization. If successful, the technology could be pivotal for humanity's long-term goal of becoming a multiplanetary species. As the technology matures, discussions regarding the ethical, legal, and logistical frameworks for colonizing other planets will intensify, encompassing planetary protection protocols and resource management. 4. Advancements in propulsion technologies. The research and development surrounding plasma propulsion may inspire further innovations in propulsion technologies such as nuclear, thermal, or ion drives, leading to even faster and more efficient space travel options. Conclusion. The development of Rosatom's plasma electric rocket engine is poised to transform our approach to space exploration.
particularly in terms of speed and safety for human travel to Mars and beyond.
The next decade will be critical in testing and refining this technology, with implications that could reshape humanity's presence in space for generations to come. By 2040 and beyond, we may witness the dawn of a new era in space exploration characterized by interplanetary travel and the potential for human colonization of other celestial bodies. The successful integration of plasma propulsion technology into our space travel capabilities could indeed mark a pivotal moment in human history.